Hello again, guys. We're here in 14.8 to talk about proofs using coordinate geometry. You can prove geometric relationships using what we know about figures in the coordinate plane, and we're going to talk a little bit also about how we make things easier. So please work through problem 1 and then come back so we can talk about why it's advantageous to use the values of 2b and 2a as opposed to just a value of b and a value of a. Alright guys, when we look at problem 1 and we look at why it's easier to use these values of 2b and 2a, we got to look at what we're trying to prove. We're trying to prove that these segments are all equal, so essentially we're trying to find midpoints. When we're trying to find the midpoint of something, you know you're going to half things or divide by 2. So since we're going to be dividing by 2, it's much easier to use a value of 2a or 2b because then I come out with a value of just AB as opposed to using fractions. So the base answer here is that the factor of 2 avoids any fractions. Try to work through A, B, and C to work this proof in number 1 and then come back to check your work. When we look at finding the coordinates of M and N, we can start by finding the y coordinates by comparing it to our y value of 2b. Since I know that it's a midpoint, it'll be half of that, so the y values would only be b. Likewise, I can find the x values by comparing the negative 2a and the positive 2a to know that these are both only a away from the y-axis. So we would have points of negative ab and positive ab. When we are looking for the distance of Pn and Rm, we know that we're just looking for the lengths of these diagonal lines, so we can use our distance formula, and once we apply that, we find our values of radical 9a squared plus b squared. Our distances here are actually congruent because what we've done is create a trapezoid. I've shown it here by connecting the lines m, or the points mn, but what we actually have is an isosceles trapezoid. Since we started with an isosceles triangle, once you connect the midpoints, you have an isosceles trapezoid. And we know that trapezoids have diagonals that are the same length. Go ahead and try to work the proof of the triangle midsegment theorem. We already talked about it in 14.7 if you remember, especially if you still have it in your notes. But if not, go ahead and try to work that. You should have the image there on your screen already. Since we already talked about it in 14.7, I'm not going to really spend much time discussing it, but as you can see there, we find the midpoints, and we then are able to, through our process, show that in fact Mn is half the length of PR. Go ahead and try number 2 here, pause the video, work it through on your own, and then come back to verify your solution. Alright, in case you guys forget, right here is our distance formula. We are finding the change in x and the change in y, and then figuring it out diagonally. So for part A, our lengths come here from b minus a negative a, which really gives us b plus a squared, and then plus c because c minus 0 is just c. Same thing for a minus a negative b, that's how we get a plus b squared, and then same rule for c, c minus 0 is just c squared. Then for c, the distance formula showed us that we have equal lengths, so that then tells me that EG is congruent to FH. Go ahead and try number 3 on your own, pause the video, and then come back just to verify once you are done. Alright, so we want to put a rectangle in the coordinate plane with P at 0, 0, so we could honestly choose any quadrant to be in, but it's easiest if we go in the top right quadrant. So we have P, Q, R, S, and then we want to find the coordinates of Q, R, and S. So Q only goes vertically, S only goes horizontally, and R combines both movements. So we have OB, R is AB, and S is a 0. We want to write the given and prove statements. Well, if we're talking about this being a rectangle, and we want to prove that the diagonals of the rectangle are congruent, then our given is we have rectangle PQRS, and we want to prove that PR is congruent to SQ. Then we need to write a coordinate proof, so we can use our distance formula here if you would like. But the coordinate proof that we have written is right there, showing the distance of PR, SQ, and showing that they are congruent. Try 4 and 5 on your own and come back to check your answers. Alright, so when we're talking about placing a rhombus on the coordinate plane, we want the vertices to be on the axes to make our life easy. So a nice easy thing to do is place our vertices on the x and y axes so that the axes are the diagonals. In 5, we're talking about a classmate placing a trapezoid on the coordinate plane. And we're going to talk about what's their mistake. Well, when I look at this, it just looks kind of fishy. This length right here and the slope does not look to be the same as this. And that would have to be true given the vertices that he chose. They would have to be the same because he assumed that it was an isosceles trapezoid. It does not look like one, and therefore his points are probably incorrect. All right, if you would like some extra practice, go ahead and try 6 through 18 on your own and come back for just the answers because we can talk about these in class. I'm just going to show you the answers for right now so that if you guys have questions, we actually have a conversation. All right, as promised, here are all of your answers. So 6 through 10 are all yes, actually. We use distance, slope, and midpoint formulas for most of them. Then after that, the answers start to get a little bit varied. All right, and from here, we only have one more problem to do. So we're going to look at 19, writing a proof. The image did not make it into your notes, but here it is right here. We want to use our coordinate geometry to prove that this quadrilateral formed by the midpoints is in fact a rhombus. So go ahead and try that, and then I will come back with the answer to chat through real fast. All right, it's a little bit lengthy of a process, but we go ahead and take this bottom left point and we make that our origin. And then we work through this process by placing my points on the axes as much as possible. So I've got T and U on the axes, and then W and V aren't too bad because W and U share an X value point and V and T share the Y value point. So we want to prove that T, W, V, U is a rhombus. So we go ahead and use our midpoint formulas, find the points of T, U, V, and W, and then we find the slopes of them. Now to be a rhombus, we want their slopes to be the same, so we see that TW and VU have the same slope, and then WV and UT have the same slope. Sorry, my images got a little glitchy there for a second. So we have our slopes that are the same here. We have pairs of parallel lines, and then we know that the lines that would connect the points of what I want to be a rhombus would in fact be perpendicular because I know that they are the same slopes as my axes. So since they are perpendicular and they are the diagonals, that makes that shape a rhombus. So this was all I really had for you guys today. Not a big lesson, but please make sure that you understand everything in Chapter 14. You want to really be confident in all this so you're ready for the test, so please let me know if there's anything I can do to help you out. Other than that, I will see you guys in class. Have a great day.